Welcome. Today we're diving into the fascinating world of communication systems. Communication is all about transferring information from one place to another, whether it's a simple conversation or a complex data transfer across continents. In our daily lives, we rely on communication systems for everything from phone calls to streaming videos. But what exactly makes up a communication system? Let's start by exploring the essential elements that allow information to travel efficiently and reliably, setting the stage for our deeper journey into signals, noise, and more. The heart of every communication system are a few fundamental elements. These include the information source, the transmitter, the transmission medium, the receiver, and the destination. The information source generates the message, which is then converted into a signal by the transmitter. This signal travels through a medium like a wire or the air, before reaching the receiver, which reconstructs the message for the destination. Each element plays a crucial role in ensuring the message gets from point A to point B with minimal loss or distortion. Journey begins with the information source. This could be a person speaking, a computer sending data, or even a sensor measuring temperature. The source is responsible for creating the original message that needs to be communicated. Without a clear and accurate source, the entire communication process would be meaningless. It's the starting point for every signal that travels through a communication system. Once the information is generated, the transmitter steps in. Its job is to convert the message into a signal suitable for transmission. For example, your voice is turned into electrical signals by a phone's microphone. The transmitter may also encode or modulate the signal to make it robust against interference. This step is vital for ensuring the message can travel long distances without losing its integrity. Transmission medium is the physical path the signal takes from transmitter to receiver. This could be a coaxial cable, optical fiber, or even the air itself in the case of radio waves. Each medium has its own characteristics, affecting how signals travel and how much noise or interference they might encounter. Choosing the right medium is crucial for efficient and reliable communication. After the signal journeys through the medium, it arrives at the receiver. The receiver's job is to capture the incoming signal and convert it back into a form understandable by the destination. This might involve amplifying weak signals, filtering out noise, and decoding the message. The receiver ensures that the original information is accurately reconstructed at the end of the communication chain. Finally, the destination is where the message is delivered. This could be a person listening to a call, a computer receiving data, or a display showing information. The destination completes the communication process, ensuring the original message reaches its intended audience. Every element from source to destination must work together seamlessly for successful communication. Communication systems can be broadly classified into analog and digital types. Analog communication uses continuous signals that vary smoothly over time, like traditional radio or telephone calls. Digital communication, on the other hand, uses discrete signals, usually represented by binary code. Each approach has its own strengths and weaknesses, and the choice depends on the application and desired quality. Analog communication systems transmit information using signals that change smoothly and continuously. Examples include AM and FM radio, where sound waves are converted into electrical signals that vary in amplitude or frequency. Analog systems are simple and can handle a wide range of frequencies, but they are more susceptible to noise and signal degradation over long distances. Digital communication systems use discrete signals, typically represented by zeros and ones. This approach is the backbone of modern technology, including computers, smartphones, and the internet. Digital signals are less affected by noise and can be easily compressed and encrypted, making them ideal for high-speed, secure communication. However, they require more complex processing and equipment. Baseband signals are the original signals generated by the information source. These signals occupy a frequency range starting from 0 up to a certain maximum value. For example, the electrical signal from a microphone is a baseband signal. Baseband transmission is suitable for short distances, like within a computer network, but not ideal for long-range communication due to signal loss. Passband signals are created by shifting baseband signals to higher frequencies, making them suitable for transmission over long distances. This is achieved through modulation, which we'll discuss soon. Passband signals are essential for radio, television, and wireless communication, as they can travel farther and are less prone to interference. Modulation is the process of altering a carrier signal's properties such as amplitude, frequency, or phase to encode information. This allows baseband signals to be transmitted as passband signals over long distances. Modulation helps in efficient use of the spectrum, reduces interference, and enables multiple signals to share the same medium. There are several types of modulation, each with its own method of encoding information. The main analog modulation techniques are amplitude modulation (AM), frequency modulation (FM), and phase modulation (PM). Each type changes a different property of the carrier signal to represent the original message, offering unique advantages and trade-offs. Amplitude modulation, or AM, involves varying the amplitude of the carrier signal in proportion to the information signal. This technique is widely used in AM radio broadcasting. While AM is simple and cost-effective, it is more susceptible to noise and interference compared to other methods. Frequency modulation, or FM, changes the frequency of the carrier signal according to the information signal. FM is commonly used in FM radio and television sound. It offers better noise immunity than AM, making it ideal for high-fidelity audio transmission. Phase modulation, or PM, involves varying the phase of the carrier signal in line with the information signal. PM is less common in everyday applications but is important in digital communication systems. It provides good noise resistance and is often used in combination with other modulation techniques. Transmission medium is a critical part of any communication system. Common media include coaxial cables, optical fibers, and radio waves. Each medium has unique properties affecting speed, capacity, and susceptibility to noise. Understanding these basics helps in choosing the right medium for different communication needs. Coaxial cables are widely used for transmitting television signals and internet data. They consist of a central conductor, insulating layer, metallic shield, and protective outer layer. Coaxial cables offer good protection against electromagnetic interference and are suitable for medium-distance communication. Optical fibers use light to transmit data at incredibly high speeds over long distances. They are immune to electromagnetic interference and offer massive bandwidth, making them ideal for internet backbones and high-speed networks. However, installation and maintenance can be more complex and costly. Radio waves are used for wireless communication, including radio, television, and mobile phones. They can travel long distances and penetrate obstacles but are more prone to interference and signal fatting. Radio waves are essential for mobile and satellite communication. Noise is any unwanted signal that interferes with the transmission and reception of the desired message. It can distort or mask the original signal, leading to errors and loss of information. Understanding noise is crucial for designing robust communication systems that can withstand real-world challenges. There are several types of noise in communication systems. Thermal noise is caused by the random motion of electrons in conductors. Intermodulation noise arises when signals mix and create unwanted frequencies. Crosstalk occurs when signals from one channel interfere with another. Each type of noise affects communication differently and requires specific mitigation strategies. Noise can originate from various sources. Natural sources include lightning and cosmic radiation, while man-made sources range from electrical appliances to industrial machinery. Even the components within a communication system can generate noise. Identifying and minimizing these sources is key to improving signal quality. Noise can have several negative effects on communication. It can cause distortion, reduce clarity, and even result in complete loss of information. In digital systems, noise can lead to bit errors, while in analog systems it may cause static or hissing sounds. Effective noise management is essential for reliable communication. Signal-to-noise ratio, or SNR, is a measure of how much desired signal is present compared to background noise. A higher SNR means a clearer, more reliable signal. SNR is a critical parameter in both analog and digital communication, influencing everything from audio quality to data transmission rates. There are several ways to improve the signal-to-noise ratio in a communication system. These include using better shielding, high-quality components, and advanced error correction techniques. By boosting SNR, we can achieve clearer audio, faster data rates, and more reliable connections. Analog and digital systems respond differently to noise. In analog systems, noise directly affects the quality of the signal, leading to gradual degradation. In digital systems, noise can cause errors, but error correction and detection techniques can often recover the original message. This is one reason why digital communication is preferred for many modern applications. Bandwidth refers to the range of frequencies a communication system can transmit. Higher bandwidth allows for faster data transfer and better quality. However, increasing bandwidth can also make systems more susceptible to noise and interference, so a balance must be struck based on the application. Multiplexing is a technique used to send multiple signals over a single communication channel. This increases efficiency and makes better use of available bandwidth. Common methods include time division multiplexing (TDM) and frequency division multiplexing (FDM), each with its own advantages. Time division multiplexing, or TDM, divides the channel into time slots with each signal assigned a specific slot. This method is widely used in digital communication such as telephone networks and computer systems to efficiently share resources. Frequency division multiplexing, or FDM, assigns each signal a different frequency band within the channel. This technique is common in radio and television broadcasting, allowing multiple stations to operate simultaneously without interference. Error detection techniques help identify mistakes in transmitted data. Common methods include parity checks and checksums. These techniques are essential for ensuring data integrity, especially in digital communication systems where accuracy is critical. Error correction goes a step further by not only detecting but also fixing errors in the received data. Techniques like forward error correction (FEC) and automatic repeat request (ARQ) are widely used in digital communication to maintain high reliability. Encoding transforms the original message into a format suitable for transmission, while decoding reverses the process at the receiver's end. Proper encoding and decoding are vital for minimizing errors and maximizing efficiency in communication systems. Channel capacity defines the maximum amount of information that can be transmitted over a communication channel. Factors like bandwidth, noise, and signal power all influence capacity. Maximizing channel capacity is a key goal in communication system design. Sampling is the process of converting a continuous analog signal into a series of discrete digital values. The sampling rate must be high enough to capture all the important details of the original signal, following the Nyquist theorem. Proper sampling is essential for accurate digital representation. Quantization is the next step after sampling, where each sampled value is rounded to the nearest level within a finite set. This process introduces quantization noise, but it's necessary for digital storage and processing. The number of quantization levels affects the accuracy and quality of the digital signal. Pulse code modulation, or PCM, is a widely used method for digitizing analog signals. It involves sampling, quantization, and encoding the signal into a binary format. PCM is the foundation of digital audio in telephony and music recording. Managing noise in communication channels involves a combination of hardware and software solutions. Shielded cables, error correction codes, and adaptive filtering are just a few techniques used to minimize noise and maintain signal integrity. Wireless communication uses electromagnetic waves to transmit information without physical connections. This includes technologies like Wi-Fi, Bluetooth, and cellular networks. Wireless systems offer flexibility and mobility but must address challenges like interference and security. Satellite communication enables long-distance data transfer by relaying signals between ground stations and satellites in orbit. It's essential for global broadcasting, navigation, and remote connectivity. Satellite systems must overcome delays and signal loss due to the vast distances involved. Modern communication systems are rapidly evolving with trends like 5G, the Internet of Things, IoT, and cloud-based services. These advancements promise faster speeds, greater connectivity, and smarter networks, shaping the future of how we communicate. Despite technological progress, communication systems face ongoing challenges. These include managing bandwidth, reducing noise, ensuring security, and maintaining reliability. Engineers and researchers continue to innovate, seeking solutions to these complex problems. In summary, communication systems are intricate networks that connect our world. From the basic elements to advanced technologies, understanding how signals travel, how noise affects them, and how we overcome these challenges is key to appreciating modern communication. As technology advances, so too will our ability to share information quickly, securely, and efficiently.